Wild ride today through the world of physics.
Oh, yeah, this is going to be a fun one.
You guys sent in some awesome sources
Really cool stuff.
all about quantum mechanics, particle physics, even string theory,
Oh,
and black holes. It's a lot.
it's a lot to unpack. Yeah,
But that's what we're here for. To
absolutely.
break it all down.
Make it fun.
And hopefully make it a little mind-blowing, too.
I think it's going to be mind-blowing no matter what.
I think so, too. Now, what I find so fascinating is how these topics,
Yeah,
they kind of seem separate at first,
right, they do.
but they're all deeply connected.
Oh, yeah, they all fit together to paint this incredible picture of the universe.
Exactly. From the tiniest particles to these massive structures like galaxies.
Everything in between.
Now, I gotta admit, some of this stuff,
Yeah.
like string theory with its multiple dimensions,
Oh, yeah.
it's a little mind-bending,
It's definitely mind-bending.
to say the least.
A little bit, yeah.
So where do we even begin?
Well, I think a good place to start is with the building blocks of the universe.
Okay.
You know, those fundamental pieces that make everything up.
Like the tiniest Legos.
Exactly. And those pieces are described by quantum mechanics and particle physics.
And we're talking smaller than atoms here.
Way smaller. We're going down to the subatomic level.
I'm already intrigued. What's going on down there?
Okay, well, at that level, we encounter the standard model of particle physics.
Okay, the standard model.
Yeah, this is our best current explanation for the fundamental particles and forces that make up everything.
Okay, so if atoms are like these tiny Legos, what are the even tinier pieces that make them up?
So it's like this atoms are made of even smaller particles called protons, neutrons, and electrons.
Oh, yeah. Okay,
Yeah.
back to high school chemistry.
Right, exactly.
Right.
But it turns out those particles are made up of even tinier particles called quarks and leptons.
Okay, so quarks and leptons, these are like the real VIPs of the particle world.
You got it. These are the fundamental building blocks of matter as we know it.
So these quarks and leptons, they're just hanging out down there.
Well, not exactly. They're constantly interacting with each other through fundamental forces.
Ah, forces. So is this where physics gets interesting?
Oh, yeah. It gets very interesting because these forces are mediated by yet another type of particle called gauge bosons.
Hold on, we're already talking about multiple types of particles.
I know, right? It gets kind of crowded down there.
We've got quarks, leptons, now gauge bosons.
Right.
It's a lot to keep track of.
Don't worry, we'll break it down.
Okay, so what are these gauge bosons all about?
Gauge bosons are like the messengers of the particle world. They carry the forces that govern how particles interact.
Okay, so they're like the mail carriers of the subatomic world.
Uh-huh, yeah, kind of. For example, photons. The particles of light are gauge bosons that mediate the electromagnetic force.
Oh, so that's how light works.
Exactly. The electromagnetic force is responsible for everything from electricity and magnetism to the light we see.
So it's all connected.
It's all connected.
Okay, this is starting to make sense. We've got these matter particles like quarks and leptons, and then we've got force-carrying particles like photons.
That's the basic picture.
But how does quantum mechanics come into play?
Ah, yes. Quantum mechanics.
That's all about the weird and unpredictable behavior of particles, right?
I got it. Quantum mechanics tells us that at the subatomic level, the rules of the game are completely different from what we experience in our everyday world.
So things get strange down there.
Very strange. For example, particles can behave like waves.
Like waves in the ocean.
Kind of,
Oh.
but it means they don't have a definite location. They're spread out like a wave.
Okay, so they're not little billiard balls bouncing around.
Nope, they're more like fuzzy clouds of probability.
Okay, that's a little weird, but keep going.
Another weird thing is they can exist in multiple states at once.
Multiple states at once. I don't even know what that means.
It's one of the key concepts in quantum mechanics called superposition.
Superposition.
Yeah, it means that a particle can be in multiple states simultaneously until it's measured.
So like it's both here and there at the same time.
Exactly. It's like a coin spinning in the air. Before it lands, it's both heads and tails at the same time.
Wow, that's trippy.
It is. And the act of measuring forces the particle to choose one state or the other.
So it's like the universe is playing a cosmic game of chance with these particles.
Oh, you could say that.
This is wild. So we've got these particles acting all bizarre and unpredictable, and they're interacting through these fundamental forces. But how does this all connect to the big picture of the universe?
That's where things get really interesting. You see, physicists have this grand ambition, the quest for a theory in everything.
A theory of everything. That sounds pretty ambitious.
It is. It's the search for a single framework that can explain all the forces and particles in the universe, from the smallest quantum scales to the largest cosmological structures.
Wow. So we're talking about unifying all the laws of physics into one ultimate cosmic rulebook.
Exactly. And that's where this fascinating but complex idea called string theory enters the stage.
String theory. All right, let's hear it.
String theory attempts to reconcile quantum mechanics, which governs the microworld, with general relativity, Einstein's theory of gravity that describes the universe on a large scale.
Okay, so it's like the bridge between the really small and the really big.
Exactly. And string theory does this by suggesting that all the fundamental particles we've been discussing, quarks, leptons, gauge, bosons, they're not actually point-like particles, but tiny vibrating strings.
Wait, so instead of little dots, these particles are like tiny pieces of string.
That's the basic idea. And these strings can vibrate in different ways.
Okay, like a guitar string.
Exactly. Just like a guitar string can produce different notes depending on how it vibrates in string theory, the different ways these strings vibrate determine the properties of the particles we observe.
So everything in the universe is made up of these tiny vibrating strings, and their vibrations create the symphony of particles and forces we observe.
That's a beautiful way to put it. It's like the universe is a giant cosmic orchestra.
I love that analogy. Okay, but here's where I get lost. String theory also talks about extra dimensions.
Right.
Like more than the 3 dimensions we can see.
Exactly. String theory requires the existence of extra dimensions beyond the 3 spatial dimensions and 1 time dimension we experience.
Okay, now you're really blowing my mind. How can there be more dimensions than the ones we can perceive?
It's hard to visualize, but the idea is that these extra dimensions are curled up so small that we can't detect them directly.
So it's like there's a whole hidden reality beyond our perception.
It's a captivating concept for sure.
But if these strings are so tiny and these extra dimensions are hidden, how can we even test if string theory is true?
That's one of the biggest challenges with string theory. It's incredibly difficult to test experimentally because the energies required are far beyond what we can currently achieve.
So it's still very theoretical.
Very much so. But even if it turns out not to be the ultimate theory of everything, it's sparked incredible breakthroughs and given physicists new ways to think about gravity and quantum mechanics.
I can see how it would be a powerful tool, even if it's not the final answer.
Definitely. And it leads to some profound questions about the nature of reality itself.
Well, my brain is definitely feeling a little stretched after all that.
Yeah, string theory can do that to you.
But it's been fascinating. So we've explored the subatomic realm with quantum mechanics and particle physics, and we've dipped our toes into the mind-bending world of string theory.
And this is just the beginning. We haven't even touched on the amazing discoveries in astrophysics and cosmology.
Oh, yeah. That's where we get to talk about black holes, dark matter, and all that cool stuff, right?
Exactly. Those are some of the biggest mysteries in the universe, and we'll delve into them in the next part of our deep dive.
I can't wait. This is going to be epic.
Welcome back to the deep dive. Last time we were exploring that wild world of particle physics.
Oh, yeah.
And even got into string theory.
I know string theory blew my mind a little bit.
It's pretty wild stuff.
But I'm ready for more.
All right, well, let's dive into some of the biggest mysteries in the universe then.
Okay, bring it on.
Let's talk about dark matter and dark energy.
Ooh, yeah, these invisible forces that seem to be shaping the universe.
Exactly. They're these invisible forces, but they have a huge influence on everything around them.
I know, we know they're out there.
Right.
Because of their effects on things we can see.
Yeah, like stars and galaxies.
But they're still shrouded in this mystery.
Totally, and that's what makes them so fascinating.
So let's start with dark matter.
Okay.
You mentioned before that it acts like invisible scaffolding.
Yeah.
Holding galaxies together.
Right.
Can you, elaborate on that a little?
Sure. One of the main pieces of evidence we have for dark matter comes from the way galaxies rotate.
Okay. How do they rotate?
Well, we can measure the speed of stars as they orbit the center of a galaxy.
Okay.
And if you just look at the visible matter, the stuff we can see, those stars should be moving much slower than they actually are.
Oh, really? So something's giving them an extra push?
Yeah, like an extra gravitational boost. And that's where dark matter comes in.
Okay.
It doesn't interact with light, so we can't see it directly.
Right, it's dark.
Right, exactly. But it has this gravitational pull that affects those stars.
So it's like this cosmic ghost just lurking out there, exerting its influence.
I like that. A cosmic ghost.
But
But yeah, that's the idea.
if we can't see it, how do we even know where to look for this dark matter?
Well, one way is through a phenomenon called gravitational lensing.
Gravitational lensing, what's that?
Okay, so imagine you have a distant galaxy way out there in space.
Okay.
And then in front of it, there's a massive cluster of galaxies closer to us.
Okay, I'm picturing it.
All right, so the gravity of that foreground cluster bends the light from the background galaxy.
So it's like a giant magnifying glass in space.
Exactly. And by analyzing how that light is distorted, we can map out where the mass is in that foreground
Yeah,
cluster.
that's smart.
Yeah. And what we find is there's way more mass than we can account for with just the visible matter.
So that missing mass must be the dark matter.
You got it. That's the evidence for dark matter lurking in those clusters.
Wow, so it's like a cosmic detective story. We're using the clues from this distorted light to track down this invisible culprit.
I like that.
Are there any other ways we can detect dark matter?
Oh, yeah. There are other clues, too. Like another clue comes with the cosmic microwave background radiation, or CMB for short.
CMB. Okay, remind me what that is again.
So the CMB is basically the faint afterglow of the Big Bang.
Wow, so we're talking about light that's been traveling through space for billions of years.
Exactly. It's amazing. And it gives us this snapshot of the early universe.
That's incredible. What does it tell us about dark matter?
Well, the pattern of tiny temperature variations in the CMB reveals a lot about the early universe,
Okay.
including how matter and energy were distributed back then.
Okay.
And to explain those variations, we need to include dark matter in our models.
So it's like the CMB is a cosmic fingerprint that's telling us dark matter was there from the very beginning.
Precisely. It's another piece of the puzzle that points to the existence of dark matter.
Wow, this is getting more and more intriguing.
Oh, yeah, and we haven't even talked about what dark matter is actually made of yet.
Okay, yeah, that's a big question. What is this stuff?
That's the million-dollar question.
Yeah.
We haven't directly detected dark matter particles yet,
Oh.
but physicists have come up with some pretty interesting candidates.
Ooh, okay. Let's hear about these candidates.
One possibility is something called weakly interacting massive particles, or WIMPs for short.
WIMPs. I like that name.
Yeah, it's sketchy, right?
Yeah.
So these hypothetical particles would only interact with regular matter through the weak force in gravity.
Okay, and the weak force is...
It's one of the four fundamental forces, but it has a very short range, and it's pretty weak.
Okay, so these WIMPs are very shy and don't like to interact with others much.
Exactly. They're like cosmic ninjas slipping through our detectors, unnoticed.
I love that analogy. So are scientists trying to catch these cosmic ninjas?
Oh, yeah. There are experiments all over the world trying to detect WIMPs, but it's really tough.
I bet. What about other candidates?
Well, another possibility is something called axions.
Axions.
Yeah, these are much lighter than WIMPs, but they also interact very weakly with ordinary matter.
So we've got the heavyweights and the lightweights in the running.
That's a good way to put it. And then there are sterile neutrinos.
Sterile neutrinos.
Yeah, remember we talked about regular neutrinos earlier?
Oh, yeah, those super tiny particles that are almost impossible to detect.
Right, exactly. Well, sterile neutrinos are even more elusive.
Even more elusive. How is that possible?
They wouldn't even interact with the weak force at all.
Wow, so they're like the ultimate cosmic ghosts.
You could say that.
It sounds like finding dark matter is going to be a really tough challenge.
It definitely is. But scientists are coming up with all sorts of creative ways to try to detect it.
Well, good luck to them. This is a fascinating mystery.
It really is. But for now, let's move on to the other dark force at play.
Okay.
Dark energy. This is the force that's pushing the universe apart at an accelerating rate.
Yeah, I know this one's really weird. Like something is overriding gravity and stepping on the cosmic gas pedal.
Yeah, that's a good way to picture it. And that something is dark energy.
But we still don't know what it is, right?
Nope, it's a complete mystery.
So how do we even begin to explain it?
Well, one possibility is that it's something called a cosmological constant.
Okay.
This is a form of energy that's inherent to the vacuum of space itself.
So you're saying that even empty space has energy?
That's the idea. It's kind of mind-blowing, but it's a prediction of quantum field theory.
Okay, so even nothingness is buzzing with quantum activity?
In a way, yes.
But is a constant energy level the only explanation for dark energy?
Not necessarily. Another possibility is that dark energy is something more dynamic, something that changes over time.
Okay, so something that's not constant.
Right, and this is where the idea of quintessence comes in.
Quintessence? That sounds like something out of a Harry Potter book.
Yeah, it's got a magical ring to it, doesn't it?
Yeah.
But quintessence is a hypothetical form of dark energy that could evolve over time.
So it could change the fate of the universe.
Exactly. Depending on how quintessence evolves, it could lead to different scenarios for the ultimate fate of the universe.
Okay, like what kind of scenarios?
Well, if dark energy is a cosmological constant, then the universe will just keep expanding forever at an accelerating rate.
Okay.
Eventually, everything will be so spread out that the universe will become cold, dark, and empty.
Ooh, that sounds kind of sad. The big freeze.
Yeah, not a very happy ending.
Are there any other options?
Well, if a dark energy is something like quintessence, things could get more interesting.
Okay, more interesting. How?
So if its energy density increases over time, it could eventually rip apart everything in the universe.
Rip apart everything. Like, what do you mean?
I mean, everything. Galaxies, stars, even atoms. That's the big rip scenario.
Yikes. That sounds pretty terrifying.
Yeah, it's not a good way to go.
Are there any more optimistic possibilities?
Well, if quintessence's energy density decreases, then the expansion could slow down
Okay.
and eventually reverse, leading to a big crunch where the universe collapses back in on itself.
Oh, so it's like the universe is breathing, expanding, and then contracting.
Exactly. A cosmic inhale and exhale. And then there are even more exotic scenarios, like a big bounce, where the universe cycles through periods of expansion and contraction over and over again.
Wow, it's like the universe is a cosmic playground with all sorts of mind-boggling possibilities.
It really is. And that's why understanding dark energy is so crucial. It holds the key to understanding the ultimate fate of the universe.
Okay, so we've got this cosmic tug-of-war going on between dark matter holding things together and dark energy pushing them apart.
Right.
But how do they connect to the larger structures in the universe, like galaxies and black holes?
Oh, that's a great question. And it brings us back to the interconnectedness of all these areas of physics.
Okay, I like where this is going.
For example, dark matter is thought to play a crucial role in the formation of galaxies.
Oh, really? I didn't realize that. How does that work?
So after the Big Bang, the universe was filled with this nearly uniform soup of matter and energy.
Oh, okay.
But there were tiny fluctuations in this soup.
Tiny fluctuations.
Yeah, like little ripples.
Okay.
And these fluctuations, amplified by gravity, began to draw matter together.
So these tiny fluctuations acted like seeds for the formation of structures.
Exactly. And because dark matter interacts mainly through gravity, it played a key role in this process.
Okay, I'm following.
It formed these vast halos around
The
galaxies.
liz of dark matter.
Yeah, and these halos acted like gravitational wells, pulling in regular matter and helping galaxies take shape.
So dark matter provided the framework for galaxies to form.
You got it. It's like the scaffolding that holds everything together.
And then regular matter clumped together within those halos to form stars and planets.
Exactly. It's a beautiful cosmic dance between dark matter and regular matter.
And what about black holes? Where do they fit into all of this?
Ah, yes, black holes. Those are fascinating objects. And they're also connected to this cosmic story.
I know we talked about black holes earlier in the context of relativity, but I'm
Right.
curious about their role in galaxy formation.
Well, we think that supermassive black holes reside at the centers of most galaxies,
Really? Even our own Milky Way?
even our own Milky Way.
Uh,
And these supermassive black holes have a huge impact on their surroundings.
okay, how so?
They have immense gravitational pull,
Right.
and as they pull in matter, they release enormous amounts of energy.
So black holes are kind of messy eaters.
Uh-huh, you could say that. And this energy can influence the evolution of the entire galaxy.
Wow. So it's like a cosmic dance between dark matter, regular matter, and supermassive black hole.
Exactly. It's a complex and fascinating interplay of forces, and we're still trying to understand all the details.
Well, it's clear that there's still so much to learn about the universe.
Oh, absolutely. We're just scratching the surface.
I'm excited to see what new discoveries are made in the years to come.
Me too. And speaking of new discoveries, there's a lot of cutting-edge research happening right now that's pushing the boundaries of our understanding.
Oh, really?
Like what? Well, one area that's really exciting is gravitational wave astronomy.
Oh, yeah. Gravitational waves. Those are like ripples in space-time, right?
Exactly. And we can actually detect them now with these incredible instruments like LIGO and Virgo.
I remember when they made those first detections back in 2015. It was groundbreaking.
It was like we suddenly had a new sense, allowing us to listen to the universe in a whole new way.
So what's been happening since then? Have they detected more gravitational waves?
Oh, yeah. Since those first discoveries, LIGO and Virgo have detected dozens more gravitational wave events,
Wow, dozens. That's amazing. What are they detecting?
mostly from merging black holes.
So we're basically listening to black holes colliding across the universe.
We are. It's like a symphony of black holes.
That's incredible. But what are we learning from all these detections?
Each detection gives us more information about the properties of black holes.
Like what kind of information?
Their masses, their spins, how they behave during these mergers.
Oh, wow. So it's helping us to understand black holes better.
Exactly. And it's also helping us to test Einstein's theory of general relativity in these extreme environments.
So it's not just about the spectacle of these events, it's about testing our fundamental theories of physics.
Absolutely.
Hmm.
And the best part is that the field of gravitational wave astronomy is just getting started.
Really? What's next for this field?
Well, new detectors are being built all over the world,
Wow.
and even more sensitive space-based detectors are being planned.
So it sounds like we're on the verge of a golden age of gravitational wave astronomy.
I think so. It's a really exciting time to be studying the universe.
I bet. But what about those elusive dark forces?
You mean dark matter and dark energy?
Yeah, are scientists any closer to cracking those mysteries?
They're definitely working on it. The search for dark matter is more active than ever.
Okay, so what's the latest on that front?
Well, remember those candidate particles we talked about earlier?
Like the WIMPs, axions, and sterile neutrinos.
Exactly. Well, scientists are designing ever more sensitive experiments to try to detect them directly.
Wow, so the hunt for dark matter is still on.
Oh yeah, it's a big challenge, but scientists are up for it.
What about indirect detection? Are they looking for any other signs of dark matter?
Yeah, they're also searching for indirect signals.
What do you mean by indirect signals?
So if dark matter particles annihilate each other,
Annihilate, like destroy each other.
yeah, they could produce gamma rays or other particles that we could detect with telescopes.
So it's like looking for the smoke from a fire, even if we can't see the fire itself?
Exactly.
That's a great analogy. Have they found any of this cosmic smoke?
There have been some tantalizing hints from these indirect searches,
Oh, really?
but nothing conclusive yet. We're still waiting for that smoking gun signal.
Well, it sounds like the search for dark matter is a long game.
It is.
Okay.
But the payoff would be huge. It would revolutionize our understanding of the universe.
Okay, so what about dark energy? Any progress on that front?
Well, scientists are trying to tackle that mystery from multiple angles, too.
Okay.
They're conducting these large-scale surveys of the universe.
Large-scale surveys. What do you mean by that?
So they're mapping out the distribution of galaxies and measuring the expansion rate of the universe very precisely.
So it's like they're creating a cosmic roadmap.
Yeah. And these maps are giving us valuable data that will help us figure out if dark energy is a cosmological constant or something more dynamic like quintessence.
Okay, so these surveys are like time machines, allowing us to look back into the past and see how the universe has evolved over billions of years.
Exactly. And that information will be crucial for understanding the nature of dark energy.
This is all so fascinating, but I'm starting to realize how much we still don't know about the universe.
You're absolutely right. We've made incredible progress.
Yeah.
But there's still so much more to discover.
It's both humbling and exciting at the same time.
I agree. That's what makes studying the universe so captivating. It's this never-ending journey of discovery.
Well, I'm glad we could take this journey together. This deep dive has been amazing.
I've enjoyed it too.
We started with the tiniest particles, explored the mind-bending world of string theory, and we delved into the mysteries of dark matter and dark energy.
It's been quite a ride.
Welcome back to the deep dive. It's been a wild ride.
Right.
In the last two parts, we started with those tiny particles, then went into string theory.
Right, some mind-bending stuff.
And then we dove into those mysterious forces, dark matter and dark energy.
Those are some of the biggest mysteries out there for sure.
But even with all that, the journey isn't over yet.
Definitely not. The universe is always revealing new secrets.
Okay, so what's next? What's the scientific community buzzing about these days?
Well, one area that's really exciting is gravitational wave astronomy.
Oh yeah, gravitational waves, those ripples in space-time.
Exactly. Remember LIGO and Virgo? Those detectors that can sense these waves?
Yeah, those were groundbreaking discoveries back in 2015.
Totally groundbreaking. It was like suddenly we could listen to the universe.
Like we had a new sense.
Yeah, exactly. So what's been happening since then? Well, LIGO and Virgo have detected dozens more gravitational wave events.
Wow, dozens. That's amazing.
It is. And most of them are from merging black holes.
So we're basically listening to black holes colliding across the universe.
We are. It's incredible.
That's awesome. But
Yeah.
what are we actually learning from all these detections?
Well, each detection gives us more information about black holes,
Like what?
like their masses, how fast they're spinning, and how they behave when they merge.
So we're getting a much better understanding of these mysterious objects.
We are. And it's helping us to test Einstein's theory of general relativity in these really extreme environments.
So it's not just about the spectacle, it's about testing our fundamental understanding of physics.
Exactly.
That's so cool. And you said that this field is just getting started.
Oh, yeah. There are new detectors being built around the world, and even more sensitive space-based detectors are being planned.
Wow, so we're going to be hearing a lot more about gravitational waves in the future.
Definitely. It's a really exciting time for this field.
I can imagine. But what about those other mysteries we talked about, like dark matter and dark energy? Any new leads on those fronts?
Oh, yeah. Scientists are still hard at work trying to crack those mysteries.
So what's the latest on the hunt for dark matter?
Well, remember those candidate particles we talked about, like WIMPs axions and sterile neutrinos?
Yeah.
Well, scientists are building even more sensitive experiments to try to detect them.
So they haven't given up on finding those elusive particles.
Not at all. It's a tough challenge, but they're determined.
What about indirect detection? Are they looking for other clues?
Yeah, they're also searching for indirect signals of dark matter.
What do you mean by indirect signals?
But for example, if dark matter particles annihilate each other,
Annihilate.
yeah, if they destroy each other, they might produce gamma rays or other particles that we could detect with telescopes.
So it's like looking for the smoke from a fire, even if we can't see the fire itself.
Exactly.
Have they found any of this cosmic smoke?
There have been some interesting hints, but nothing conclusive yet.
So the mystery continues.
It does.
What about dark energy? Any progress on understanding this mysterious force?
Scientists are working on it. They're conducting these massive surveys of the universe.
Massive surveys.
Yeah, they're mapping out the distribution of galaxies and measuring the expansion rate very precisely.
So it's like creating a cosmic roadmap.
Yeah, and this data will help us figure out if dark energy is a cosmological constant or something more dynamic like quintessence.
So these surveys are like time machines letting us see how the universe has evolved over billions of years.
Exactly, and that's crucial for understanding dark energy.
Wow, it's amazing how far we've come in our understanding of the universe.
It is. But it's also humbling to realize how much we still don't know.
That's a good point. It's like we're just scratching the surface of all there is to know.
Exactly. And that's what makes it so exciting. There's always more to discover.
Well said. It's been an incredible deep dive.
I agree. We covered so much ground.
We started with the tiniest particles.
Right, those fundamental building blocks.
Explored the mind-bending world of string theory.
With its extra dimensions.
And we even delved into the mysteries of dark matter and dark energy.
It's been a wild ride.
It really has, and it just goes to show the power of human curiosity and our desire to understand the universe.
Absolutely. And the best part is that the journey is far from over. There's so much more to learn and explore.
Exactly. So to all our listeners out there, keep questioning, keep exploring, and never lose your sense of wonder about the universe.
Because in the grand scheme of things, we're all part of this incredible cosmic story.
And there's nothing more fulfilling than trying to understand our place in it.
I couldn't agree more.
Thanks for joining us on this deep dive. Until next time, keep looking up and keep exploring those infinite wonders of the universe.